I'd like to start by asking you a question. Which are there more of? Natural numbers, such as 0, 1, 2, 3, etc., or real numbers, any number that fits on the number line? One could make the argument that since they're both infinite, they are the same. But is that really true? First of all, let's find a way to determine whether two sets are the same size or not. Let's compare these two sets A and B. Now we're going to map set A onto set B, where we take each element of set A and tie it to an element of set B. Now, let's take set C here and try to do a mapping between set B and set C. Note this unmapped element in set C. Comparing A and B, we can see that no element is unmapped. Thus we can conclude that A and B are of equal size. Conversely, since there's no way to map B onto C without missing an element in C, we can conclude that C is bigger than A and B. Now let's try to apply this logic to infinite sets. Take set A, which is defined as the set containing all integers, and let's compare it to set B, which is a set containing all even integers. Obviously, each element of set B is contained in set A. So if we try to do a mapping from each element n in set A to its corresponding n in set B, we would be missing some elements in set A. If, however, we took each element n in set A and mapped it to 2n in set B, we see something different. As you can see in this mapping, there are no elements in either set A or B that go unmapped. For example, any arbitrary element of set A, such as 7, would get mapped to its double in set B, in this case 14. Conversely, any arbitrary element in set B, such as 26, would get mapped to its half in set A, in this case 13. And thus we can conclude that sets A and B are the same size. And an important note for sets of infinite size is that if there exists at least one mapping that leaves no element unmapped, they are considered the same size, even if there exists another mapping that leaves some unmapped elements. Now we are ready to tackle the initial question, whether there is a mapping between the natural numbers and the real numbers. First, let's write the natural numbers over on the left here. Then, next to each natural number, we're going to write out a real number to form some arbitrary mapping. Note that while we've only written out so many here, there will be infinitely many of these. Now, we're going to underline one digit from each real number in a diagonal pattern like this. Then, we are going to construct a real number where each digit is different from its corresponding underlined digit. Note that this new real number differs from each of our mapped real numbers in at least one digit, and thus is a distinct real number that is unmapped. This is known as Cantor's diagonal proof, and it shows us that no matter how we try to map the natural numbers onto the real numbers, we will always be left with some unmapped real numbers. And thus we can conclude that there are more real numbers than natural numbers. Now let's move on to a different question. Say we have two sets A and B, where A contains all real numbers between 0 and 1, and B contains all real numbers. Clearly set A is not bigger than set B, but is B bigger than A, or are they the same size? To solve this, let's first define set C, that contains all real numbers between two arbitrary numbers t and s. Let's first see if there exists a one-to-one mapping from set A to set C. Note that since s is greater than t, s minus t is positive. Here we've written out the constraints of x and y, where x is an element of set A and y is an element of set C. Now we'll make the claim that we can map x to y using the equation y equals x times s minus t plus t. We know that both x and s minus t are positive, thus their product is also positive, and adding t to both sides of this inequality, we get that x times s minus t plus t is greater than t. Thus this expression has the same lower bound as y. We also know that x is less than 1, and since s minus t is positive, we can conclude that x times s minus t is less than s minus t. Again, adding t to both sides of this inequality, we get that x times s minus t plus t is less than s. Thus, our expression has the same upper bound as y. And since our function is a linear function with respect to x and y, we know it is reversible, and thus there exists a one-to-one mapping from set A to set C. And since there exists a one-to-one mapping from set A to set C, we know that they are the same size. Now we just need to find if there exists a mapping from set C to set B. Here we've written out the constraints of y and z, where y is an element of set C and z is an element of set B. Now we are going to set t to negative pi over 2 and s to pi over 2. Now we'll claim that we can map y to z using the equation z equals tan of y. To show that this mapping works, we're going to draw out the graph of this function from y equals negative pi over 2 to y equals pi over 2. Famously, this function has two asymptotes at y equals negative pi over 2 and y equals pi over 2. Thus we can see that this function maps the real numbers between negative pi over 2 and pi over 2, which is set C, onto the entirety of the real numbers, which is set B. Thus we have found a one-to-one mapping from set C to set B. And since there exists a one-to-one mapping from C to B, we can conclude that they are the same size. And since A and C are the same size, and C and B are the same size, we can conclude that A and B are the same size, thus showing that B is not bigger than A. Now for one final question. Let's define set A as the set of all points on a line segment. And set B will be defined as all the points in a square. Clearly A is not bigger than B, but are they the same size? Or is B bigger than A? First, let's establish something about infinite sets that will be useful later. To demonstrate this, let's define two countably infinite sets, C and D. Note that there exists a one-to-one mapping between these two sets. Thus we can conclude that C and D are the same size. However, if we had made the mapping like this, it would have left some elements of set D unmapped, giving the appearance that set D is bigger than set C. Conversely, if we had made the mapping like this, it would have left some elements of set C unmapped, giving the appearance that set C is bigger than set D. The fact we're establishing here is this. If there exists a mapping between two sets that leaves elements of one set unmapped, and another mapping that leaves elements of the other set unmapped, then there exists a perfect one-to-one mapping between the two sets. Now back to the square and line. Here we're going to define a way to describe any point in the square, like this point for example. Splitting the square vertically into halves, we see that our point is on the right, which we denote with a right arrow. Splitting the remaining section in half horizontally this time, we see that our point is in the upper half, which we denote with an up arrow. We do this process infinitely, giving us an infinite string of arrows that uniquely defines our point. We then keep all of the horizontal arrows as they are. We then convert all of the up arrows into right arrows, and all of the down arrows into left arrows. This gives us a unique infinite string of horizontal arrows. Now we can map this onto a point on a line. We first split our line in the middle, and take the half denoted by the first arrow, in this case right. We then repeat this process with the remaining part and the second arrow, in this case right again. Again, we do this process infinitely, closing in on a single point on our line. So we have shown how to take an arbitrary point in the square and map it to a point on a line. Now you may be wondering what happens if our point lies exactly on a dividing line. Well, for this purple point here, we first see that it's clearly in the upper right section. But now since it's on a dividing line, we claim it's in the right section. And then every other horizontal line will be left. And likewise for this pink point, which lies on a horizontal dividing line, when we need to disambiguate which part it's on, we favour the upper half, and then every other vertical arrow from there will be down. And then for something like this orange point, both of these principles will apply. So now we have a way to map every arbitrary point in the square to a unique point on the line. But can we go the other way? Let's take our line and mark 2 points on it. The first 7/12 of the way down, and the other 3/4 of the way down. Using our arrow algorithm, we can see that 3/4 can be displayed as right, right, and then infinitely many lefts. And 7/12 can be depicted as right, left, followed by left, right, left, right, left, right indefinitely. Now to translate this into our square algorithm, we have to convert half of our horizontal lines into vertical lines, right becoming up and left becoming down. Now for both of our arrow sequences, the first, third, fifth, seventh, etc. arrows will remain horizontal. And then the second, fourth, sixth, eighth, etc. arrows will be converted into vertical. Now we can take these two arrow sequences and map them onto the square. We'll denote this top sequence as orange and this bottom sequence as pink. Now, following the orange sequence, we see that it first takes the bottom right quadrant and then forever moves to the top left, eventually mapping to the center of the blue square. And following the pink sequence, we see that it first takes the top right quadrant and then forever moves to the bottom left, again mapping to the center of the blue square. This means that we have 2 points on the line that would map to the same point in the square. Now, had we started with this point in the square and tried to map it to a point on the line, we would have seen that the arrow sequence would be right, up, followed by all lefts and all downs, meaning it would have mapped to the pink point, which was 3/4 of the way down the line, meaning the orange point, 7/12 of the way down the line, would have been unmapped. Thus, we have shown that our mapping earlier from the square to the line has left some points on the line unmapped. Thus, we have a mapping that makes set A appear bigger than set B. However, had we tried to map the line onto the square like this, it is blatantly obvious that there are points on the square that are unmapped, and thus set B appears bigger than set A. But remember what we established earlier. Since there's a mapping in which A looks bigger, and another mapping in which B looks bigger, there must be a perfect one-to-one mapping in the middle, and thus set A and set B are in fact the same size. Now the real question is, does there exist a mapping from a square to a cube?